A very good morning, children. In the yesterday's session, we had learned the last conclusion points about the edge length in the three types of packing efficiency, like simple cubic, body centered, and the face centered. In this, when we had given the edge length A is equal to 2R, whereas in case of face centered cubic units 2 into 2R, 2 into root R, where A is equal to 4R by root 3. 4R by root 3. Those are the three data that we had learned. Other than that, what had we learned still? We had learned about the radius, how to calculate. Once this is known, you can easily get the radius. Is it not? And how about the BCC? Once you know this one, we can calculate the radius. How to calculate the radius in FCC? In FCC, radius R is equal to A upon 2 into root 2. Whereas in the BCC, radius is equal to root 3 into 4, root 3 into A by 4. So that's what we have learned about the radius. Still, what did you learn about the distance? Here generally distance is equal to root, how have we given the distance in FCC? Do you remember? In the case of BCC, distance is equal to 3A by 2. 3A by 2. So we had learned these points in the yesterday's session. So based on the first problem today, a metal crystallizes in FCC. The edge length is A, they had given edge length is 408 picometers. The diameter of the atom is, here D is not meant by diameter. D stands for the distance between two oppositely charged ions. But now they raised the word diameter. What is the formula to solve the diameter? We know diameter is equal to 2R. Diameter is equal to 2R. So if you know this R, how to calculate R in the FCC? R is equal to A by 2 into root 2. That's the formula that we know in general. But here we need to say 2R is equal to, what is the edge length given? 408 upon 2 into root 2. So you can cancel the 2 and 2, so you can get the R is equal to 408 upon 1.414. You solve and you give the correct option. Got it? Good. Now let's go for the second one. What is the second question given here? AB crystallizes in BCC. AB crystallizes in BCC with edge length of 387 picometers. Try to solve this problem, children. How to work with this? The distance between oppositely charged ions in case of BCC. We had already reviewed yesterday what we had learned. The distance in case of BCC, the formula is root 3 by 2 into A. So directly you can work in case of BCC. What we know, distance is equal to root 3 into A by 2. 1.732 into what is the edge length they had given? 387 upon 2. At last your unit will be picometer. I am not writing on board every time instead of writing. I am not using the word. These all units are all picometers only. Go for the next one. Copper crystallizes in FCC with 361 picometers. What is the radius of copper? Atom. So here what was given to find out what is the radius R of the copper atom. Here it is crystallizing in FCC. In case of FCC, how is the radius given as? In the case of FCC, radius is given as the A by 2 into root 2. A by 2 into root 2. What is the edge length given here? Edge length is 361 picometers. So 2 into 1.414. You saw when we check the options. I am not answering here everything. You must do. See children, we are having our next concept related to density. Related to density. It is generally represented with symbol rho. Generally represented with symbol rho. But you can do with the symboling D for in place of the rho for calculations. But rho is the correct statement. We know in PUC we have already learned this density is equal to mass per unit volume. But here we had already derived one formula for this, Z into M by A cube into ND. And you do not have special introduce for this one. This is already just a crash course type. So Z, what does Z stands for? Here in the case of Z stands for number of atoms. Z stands for the number of atoms. Don't forget, in the case of BCC you need to take 2 atoms, and in the case of FCC you need to take 4 atoms. So they will clearly mention. If they mention it is of sodium chloride type, even that time also you can say sodium chloride type is of FCC and number of atoms are 4. So this is the simple point to remember. Then what is M? M stands for the molar mass. M stands for the molar mass. That is expressed in grams mole inverse. Units, I am highlighting the point units. And AQ, first of all you must know the edge length. They will be generally giving this edge length as A. But this edge length we must convert that into, they will be giving in picometer. They will be giving in the picometer. 1 picometer is equal to 10 to the power of minus 10 centimeter. Why to convert into centimeter? Because in any of the problem, the density value, how much we will be getting, density is equal to gram cubic centimeter inverse. So in order to get that into gram cubic centimeter inverse, we are converting picometer into centimeter. Or if they have given in the form of angstrom, it is equal to 10 to the power of minus 8 centimeter. Or if they have given in nanometer, it is equal to 10 to the power of minus 7 centimeter. So these are the units that you must remember when you are working with the given edge length. How much they had given, you need to cube that into that value into, and you must cube it. And how about Na? Everyone knows this Na. You can blindly remember Na is equal to 6.023 into 10 to the power of 23 atoms mole inverse. Atoms per mole, let's say. So atoms mole inverse is the unit. So these are the units. You had developed in PhD with regarding many problems, and 2 problems I had given you. You must do this one as the homework and just send in the WhatsApp link. You practice, that's it, enough for me. A metal has FCC lattice. The edge length of unit cell is 404 picometer. The density of metal is how much have they given the density? Density is not clear there. Density is the word that is mentioned. 2.72 gram cubic inverse. 2.72 gram cubic inverse, the molar mass of the metal is. So what to do? Everything is given here. Regarding this problem, once you see, they had already mentioned the density. How much is the density, children? Density they had given as 2.72 grams. 2.7. I am not writing the units here. And Z is for FCC. How many number of atoms will be there? 4 will be there. Into molar mass. They didn't given the molar mass, but edge length is given. How much is the edge length given? 404 picometers. So 404 into 10 to the power minus 10 into whole cube into Avogadro number. You must multiply the Avogadro number. You know how to calculate the molar mass. So please work on this problem. Cesium bromide crystallizes in BCC. The unit cell edge length is 436.6 picometers. Given that atomic mass of cesium is 133 and the of bromine is 80. See here children, they didn't mention the molecular mass, they had given the atomic mass. In this case, you must sum up the atomic masses of all the given ions or elements. So how much will be the molar mass? 133 plus 80. That will be your molar mass. The density of cesium chloride is. So you can directly apply the point. So these are two of the problems that are given you as the homework. You do and practice and find the correct option. We are going for the next concept. See children, yesterday we had learned with one more concept that is called radius ratio. Radius ratio. I hope you remember this value 0.155 to 0.225 and 0.225 to 0.414. 0.414 to 0.732, 0.73 to 0.1. In this case, it is called trigonal planar type system, and it is of tetrahedral system, radius ratio that contains, whereas this is the octahedral system, and this is of cubic type. This is of the cubic type. Examples also were given: zinc sulfide, here what I had given: cesium, bromide, sodium chloride, zinc sulfide types will be mostly question. How did we got this value? We got this value as radius of cation upon radius of the anion is called as the radius ratio. Generally, cations will be very small in size. So these cations will be surrounded by anions. Our smaller size cation will try to occupy the empty space. Empty space, what did we call? Void. So here, what we are giving the word is the radius of void upon the radius of the particular atom. Means here our void, you see, these are the atoms. The space between these we call as the void. Is it not, children? The space here in between we call as the void. So this is what I am calling as smaller, and the R plus we used to call, but now we are calling this is the radius of the void, which is upon the remaining are the atoms. So the void we are going to represent the symbol smaller, and the radius of atom we are representing as the capital. So in the place of our radius ratio, now we are bringing a word R by R. What is meant by R? R stands for the void, and capital R stands for the radius of the atom or the anion. They are, if you see, the same values we apply. But here the two important areas are regarding tetrahedral, how to represent, and regarding octahedral, how to represent. These values for tetrahedral and the octahedral. R by R for tetrahedral. What is the value we had? 0.225 is for the tetrahedral, and R by R is the value which ranges for 0.414 for the octahedral. Means these are related like this. Means the radius of void to the radius of atom in the case of tetrahedral and octahedral are related like this. Because there is now the objective area which is also found on this small topic. See the question here. What is the question given here? If the radius of an octahedral void is R, and the radius of atom in the close packing R, relation between R and R is here we want to find out what type of system they have given. Octahedral system. Generally for octahedral system, how we had given R by R is equal to 0.414 of the octahedral system. But if they mention clearly for you, if they are asking R is equal to, how to find out, 0.414 into R. In case of the octahedral system, that is the relation between R and R in case of the octahedral system. And in case of tetrahedral system, R is equal to 0.225 into capital R. This is what their relation. Because this type of questions may also be seen in the NEET examination. So just want to find a relation. Then you must get that formula. Okay children, we are going for the next point. See children, after this the concept that we are going to see here is about defects in the solids or imperfections in the solids. I hope you people had already seen the data that I have forwarded you in the WhatsApp group regarding the entire synopsis, because waste of writing my stories, so I don't want to write the stories. I just want to explain once if you had a fun time. So these defects in solids or imperfections in solids, you can see the defect may be a balanced defect or it may be an unbalanced defect. If the defect is a balanced defect, we call it as under the stoichiometric defect. What do we call it as the stoichiometric defect? See, we are seeing only about point defects. We are not highlighting about aligned defects which are not there in our syllabus. So under this point defects, what is the stoichiometric defect means? They are in the balanced state. What is meant by a balanced state? Means overall, once you see the number of atoms or the mass of the substance remains constant. There will not be any imbalanced state. But metal, later on we have also classified this as the non-stoichiometric defect. Means there will not be any balanced condition. So coming for our stoichiometric defect, the only three very important defects are the Frenkel defect, Schottky defect, and the cationic vacancy. What is meant by Frenkel defect? See children, generally this is the cation and this is the anion. Cation and the anion. You can see the radius of cation and anion are not the same. There is a large difference between the radius of cation and the anion. So the systems in which there is a large difference between cationic radius and anionic radius, in such kind of systems only we can see the Frenkel defect. What is meant by this Frenkel defect? For example, if you see the cations and the anions here, some of the cations, the system Frenkel defect is seen in the systems in which there is a large difference between the radius of cation and the anion. When you see here, some of the cations will leave their site and they will occupy some interstitial site. This between space we call as the interstitial site. So the place where they used to be, it used to be left as the vacant, and it creates some vacancy. This is generally seen in the compounds where there is a large radius ratio difference, like zinc sulfide, silver chloride, silver bromide, and also silver iodide. Here the density is not affected because within the place they are moving. The cations are moving within the place. So density does not decrease or does not change. So this is what very simple point regarding our Frenkel defect. Clear? Now let us go with the Schottky defect. What is meant by Schottky defect? See here, in this case of Schottky defect, the radius of cation and radius of anion will be having the same. Radius. Means you will not find much difference in their radius. Now in such compounds, like you can see sodium chloride, potassium chloride, cesium chloride, or this silver bromide is there. This silver bromide will show both Schottky defect and the Frenkel defect. So Schottky defect means what? If one cation is vacating from its site, leaving a vacancy, or some other location, on some other location. Here cation has vacated and here anion has vacated from their sides. Here the Frenkel defect we call as an interstitial defect, but here completely vacancy defect. We call it as the vacancy defect in case of the Schottky defect. Because equal number of cations and anions will be dislocated from their place, and that results in a decrease of the density, of the particular ionic compound. So this is what about the Schottky defect. In the objective, if you see, which will show both the effects, you must say silver bromide will show both the effects. Next, or the third one, for example, this is only sodium chloride. How do sodium chloride will be like? Sodium atoms are surrounded by chloride atoms already. So this sodium chloride ionic compound, once you see sodium chloride ionic compound, once you study here, if at all some other case means during solidification, means during crystallization, better term is crystallization, some of the sodium ions here are going to be replaced with strontium. Generally sodium is +1, but here which ion was replaced here? Strontium ion is replaced during crystallization. But here charge is more, one positive charge is more. In order to neutralize positive charge, one of the sodium ion will be vacated from this crystalline. So this type of defect is due to the impurity present in the sodium chloride. So they will ask, the sodium chloride having impurity as strontium chloride will show this defect. The charge is same, neutral. The total compound is neutral. Not only in this, you can also see this one, like in the case of silver chloride and cadmium chloride. Examples are very important sometimes. So this is what about a short about stoichiometric defect. Coming for the non-stoichiometric defect, I would like to say here in a shortcut like due to anionic vacancy means what? If you are having sodium chloride and you are going to heat this sodium chloride, in the sodium chloride vapor, in which case you are heating this one in the ionic compound of sodium chloride is present, you are heating that in the presence of the sodium chloride vapor. Means now surrounding this ionic compound there will be some of the sodium ions more in number. Above the ionic crystal, sodium vapors, better you can see, you are going to heat them in the sodium vapor, then your reaction will be more. How do we get sodium vapor? From the sodium chloride. So the sodium vapors, once you start heating here, some of the anions, means what are these negative charges? Negative charge is nothing but the chloride. This negatively charged chloride will try to move towards to the sodium. By giving up its electron here, means sodium is there no Na plus. When it is forming, electron will be reaching this center from the sodium, and from here chloride will be going and bonding with the sodium that is present at the surface. Obviously chloride ions will be diffused up. Here the space left by this chloride is now filled by the electron lost by the sodium. Now this is observed by a scientist called far bin center, or we are calling this one as the F center. Now due to the presence of the single electron, when some light falls on this substance, it will go on excitation. Which will go on excitation? Electron will go on excitation. Now sodium chloride appears yellow in color. This you can see one sodium is more in this one, or you can speak in another word. This vacancy is due to the movement of anion from its place, original place to another place. So we say metal is excess here, sodium is excess. After being excess, some anion has vacated its place. So in the metal excess defect, the first one what we are going to see, due to anionic vacancy. Due to anionic vacancy. Due to this anionic vacancy, the filled space which is the electron, we are finding sodium chloride as the yellow. Sodium chloride as the yellow. Similarly, you can find lithium chloride, potassium chloride also. Lithium chloride, you can see pink, and this one is the lilac or violet in color. Lilac or violet in color. These are all due to the anionic vacancy. And presence of extra cations means what? When you take a zinc oxide, metal oxide on heating, generally this is white in color. This is white in color. And now after heating, the oxygen will be left over. Half bottom, leaving more amount of zinc ions. Along with that, there will be the electrons. The electrons will absorb some color from the UV radiations and it will impart the characteristic color like yellow color for the compound. Why this is absorbed? Here also metal is more in the compound, and this is due to the presence of extra cations because oxygen had left the compound after heating. Now metal deficiency defect. Generally any metal oxide, once you see, you can write the metal oxide as MO, where M stands for the metal and O stands for the oxide. But here, strictly speaking, the metal does not have a complete ratio with oxygen. Its ratio may be ranging from 0.93 to 0.96. Such compounds will show the metal deficiency. Most of the problems will be given from this area. Numericals we can see from this area. Let us see one problem based on this metal deficiency defect. Then the concept will be clear for us. See here children, about the metal deficiency defect. Already we had introduced in the metal oxides, the metal will range from 0.93 to 0.96. Here, most of the cases will be questioned regarding the iron, ferrous and ferric. Iron present in the +2 state we call as the ferrous, whereas the iron present in the Fe+3 state we call as the ferric. Let us see one question here. The composition of a sample of bauxite whose formula is given as FeO is Fe 0.93 and oxygen 1.00. What percentage of iron is present in the form of Fe3? So generally in this kind of metal oxides, metal will try to exist in more than, means two types of oxide states also will be there. What are the two types of oxides of iron we know? Fe+2 and the Fe+3. We don't know how much of Fe+2 is there, or we don't know how much of Fe+3 is there. They are asking us to calculate what percentage of iron is in the form of Fe3, means Fe+3. So let us see here, very important and easy method of learning. In the given compound, first you try to write the given compound. What is the given compound? FeO. What is the percentage of iron here? 0.93. Oxygen is 1.00. After studying this compound, is it having any charge? Charge is 0. No charge. Charge is not mentioned. So charge is 0, we can see. So what our point here is, the metal will occur in two of the oxidation states. Let us see the iron which is in the Fe+2. It is present in hexamone. We don't know the amount. and iron that is present in the Fe plus 3 state, Fe plus 3 state. From this 0.93, if you remove the x, then the remaining will be Fe plus 3. Then the remaining will be Fe plus 3. So here, first of all, we want to know what is the x. See here, children, the total charge we need to multiply with their abundance. First thing is total charge we need to multiply with their abundance, and that must be equal to the charge. That must be equal to the charge present on the compound. Charge present on the compound. What is the charge present on the compound? Already we had said the charge present on the compound is 0. Here, before I go for the total word, let me give for individual charge and their abundance. Individual charge and their abundance. Here, what are the elements are present? One is present as the Fe plus 2, another one is present as the Fe plus 3. Oxide means everyone knows oxygen will be in the -2 oxidation state. Oxygen will be in the -2 oxidation state. What is the point I am suggesting? Charge into abundance. What is the charge of this iron? Plus 2. So you must multiply the charge of the element into its abundance. What is the abundance of Fe plus 2? We hope it is x. So 2 into x. Next element means total. We want to get total elements. Charge and abundance. First we are taking the individual elements. Fe plus 3. What is the charge of Fe plus 3? Plus 3 into. What is abundance? Let us hope its abundance is 0.93 minus x. We need to say total means you must sum up their charges. You must sum up their charges into abundance. So charge of Fe plus 3 into abundance plus charge of Fe plus 3 into abundance plus charge of oxygen is -2. What is this abundance children? What is abundance? Abundance is 1.0. 1.0 equal to total charge. Equal to total charge. Once again I am repeating. First your work is write all the elements. Then you write the charge into their abundance or availability. How to know? Here Fe occurring in two forms. So let us say Fe plus 2 is in the x abundance. Fe plus 3 is in the 0.93 minus x. And oxygen abundance is 1. You take as only 1 that was given there. There is no charge on the molecule, so that is equal to 0. So how do you get here? 2x plus 3 0.93 minus x. 3 into 0.93. How much value are getting children? I don't know. You write the value here. 0.93 minus 3x minus plus 2. It will be minus, right? Minus 2 into 1 is 2. That is equal to 0. Please help me. 0.93 into 3. 0. Or we can say 93 into 3. 3 3s are 9 and 3 9s are 27. 2.79. I am taking as 0.93. So it's 2.79 we got. So what we want, it is 2x and minus 3x is there. So I would like to say minus x. Here plus 2.793 is there, minus 2 is there. So 2x plus 2.79 is equal to 0, or x is equal to x is equal to 0.79. X is equal to 0.79. So once we get the percentage of this Fe plus 2, percentage of this Fe plus 2, how to get the obtain upon the given total 0.93 into 100. How much you are getting? You please get some value will be getting. Now if you want to know the abundance or the percentage of the iron present, already we got some, we will be getting some value here. So in order to get the percentage of the Fe plus 3, percentage is out of 100. You subtract this value, then you will be getting some value that will be equal to the percentage of the Fe plus 3. So the minimum point of view not to give up is getting this calculation of x. Then you need to first of all find out the percentage of the Fe plus 2, which will help you to get the percentage of the Fe plus 3. See children, we are having one more problem related to this type of example. Formula of nickel oxide with metal deficiency defect. Formula of nickel oxide with metal deficiency defect in its crystal is nickel 0.98 and oxygen. That didn't mention any number. Even if it didn't mention any number, it will be equal to 1. Nothing else that is equal to 1. The crystal contains Ni2 plus and Ni plus 3. The fraction of Ni2 plus ions in the crystal is, fraction of Ni2 plus ions in the crystal is, what fraction of Ni plus 2 ions are there? Here, what the things we know? What things we know? Is it having any charge in it? It is not having any charge. What type of ions are present in the crystal totally? Na plus 2 is there, Na plus 3 is there, and oxygen is minus 2. But there is no charge on the crystal. Total charge into its fraction or abundance we can speak. So Na plus 2. So we can say, let us say the nickel plus 2 is x, and from the 0.98, if we subtract some x, we can get the Na plus 3. How much of fraction is there? But the question is regarding the fraction of Na plus 2. Na plus 2. So let us speak the charge into the abundance plus the charge into its fraction, we can speak minus x plus charge is 2 and its fraction is 1. I am writing as 2. So similar fashion what we had done in the previous case, the same thing we need to follow. I hope I had given you the clue how to work with. You can solve this fraction of the compound, how much it is present. So let us say here we are going to upload for you in the WhatsApp about the total Schottky defect and Frankly defect regarding questions. You please solve all those questions and still upload for me. Few questions I am writing on the board for your clarification. See children, here one question I am giving for you. You need to solve this one. If you didn't get, you can ask me in WhatsApp. Potassium has BCC structure with nearest neighboring distance. 4.52 angstroms. Its atomic weight is 39. The density will be. Generally density whenever is given, what we know Z into M by A cube into mg. Then we can easily find out the atomic mass 39. BCC is given now. For BCC, number of atoms are 2. We will write this point. Molar mass is 39 gram mole inverse. And Avogadro number you will be knowing 6.023 into 10 to the power of 23 atoms mole inverse. But here edge length is not given. Is the edge length given? Edge length is not given. A is not given. Then what to do? When the nearest neighboring distance is given but edge length is not given. What is the nearest neighboring distance? Nearest neighboring distance can you put say in case of BCC, D is equal to how much? Root 3 A by 2 into A. So from this you can extract the edge length. See what the distance they are given? 4.52 is equal to 1.732 upon 2 into A. So by this you extract the edge length that is given in angstrom. Some value you will be getting in the angstrom. You must convert this angstrom into picometer. Don't forget 1 angstrom is equal to 10 to the power of minus 8. You can directly convert into centimeters. There is also better thing. Anyhow, you need to convert that as the edge length from 1 angstrom 10 to the power of minus 8 centimeters. And you can directly apply that into the cube form. These type of problems are very important. You solve and you send me. Thank you.